Okay, so you are able to see my screen, right? No issues.
Yeah, no issues.
Okay, okay. So, any doubts before we begin with the problems?
Yeah, doubts in the sense I just wanted a explanation of the constraint qualification. Means why it's so essential in formulating the KKT conditions. Means this is if you could clarify a bit with some examples, maybe that would help greatly.
Okay, okay. So let's maybe take. So first of all, yeah, welcome to week 8.
It's not recording, right? Okay, or
Uh,
it's recording.
1 second. Yeah, yeah, it is recording.
Oh, fine, fine. Sorry for that. Yeah.
Yeah, no issues. Yeah, so just give me a second. I'll go back to my notes. And I'll very briefly mention so what is it that we are trying to talk about. So the whole thing started with um, defining the following. So we were defining our tangent cones, right? At a point with respect to a certain set. And do you remember how we defined it?
Yeah, we are trying to defining it as an intersection of some sets, right?
No, no. So
Of
let's
simpler
take it
sets, right?
from the very first step. So how do we define for a given set? We'll come to for intersection of sets, but just for a given set, a single set.
Yeah, tangent set. Yeah, tangent set is all space, all the directions from which you can approach that point by staying within that set, right?
Correct. So how would we write it? How would one? How
Yeah.
would we?
So,
Huh?
uh, wait. I am forgetting a definition. Means,
Okay. So you are
yeah.
right.
So
Whatever you're saying, we'll just state that mathematically. So what we'll do is we'll say there exists some sequence in the set S. Okay. Such that we approach the point of intersection star, and there is a sequence tau k going to 0.
so just a small doubt. So down arrow means approaches zero from the zero
Decreases, yeah.
plus, right,
Yeah, yeah,
direction.
decreasing to the sequence, decreasing to 0, decreasing and converging to 0.
Okay.
Okay, so xk minus star, okay, equals to t. Okay. Now, so yeah, so if, for example, if you can just take this case where there is a point x are on the boundary and this is my set S, right? So how can I approach this? Many ways, right?
Yeah.
Can come in all possible ways. So basically this is going to be my this half space is going to be my tangent cone, right? But
So
so
are
the
half
yeah,
spaces
yeah.
are half spaces cones?
Half space is yes, right? So you take any
They are
point.
cones, right?
Sorry.
Yeah, they are cones. Yeah, they are cones, right. Yeah.
Okay. So let me just write it down.
Yeah.
So how would you define a half space?
So suppose a not equal to zero, all the x has that a transpose x is greater than equal to zero, or less than equal to zero. Yeah.
Okay, we'll make it slightly more general. We'll just say less than some b, right? Where
Okay.
a and b are not. Let's say a is not equal to 0.
A is not equal to zero. Yeah.
Of course. Okay, so yeah. So what do you want to check?
This is a cone.
Okay. So how will we proceed?
So it should be positive homogeneous. So you just scale it by some lambda greater than 0, and let's see.
Okay. Okay. Take lambda greater than equal to 0. Okay.
Then
So A
lambda
transpose
x,
lambda x less than equal to B. Then what can we do?
pull lambda out, right?
So yeah, assuming that lambda is positive.
Lambda is positive, yeah.
So this thing, this thing, is it always
Yeah.
necessary that it will be less than B?
No, not necessary.
Yeah, right. So it depends.
Hmm.
So what I'm trying to say is, if I were to be, let's say, here, then it's okay, right? If I were in this quadrant.
Yeah, yeah.
Okay, but how about oh, sorry. Okay, sorry, I'm giving the wrong example. Yeah, okay, let's just take this line. Somewhere it's sitting in the space. Okay, and let's say you're looking at this point. Sorry, this is the half space. Okay, and let's say we take some point here, x, and for concreteness, what I will do is I will again take the same case, but now I'll say that's the lower half. So what can we say now?
So if it's in the lower half, that means if you
Okay, let me give this case. Like, it is
uh,
slightly more general and perhaps will illustrate my point. Let's say I do this. So I want to consider 2 points. Uh, one point here. Yeah, let's just take points in all four quadrants. What will happen? And let's say when we scale that point, what will happen?
so in the from the looks of it, in the three quadrants it doesn't matter, but in the first quadrant it would matter, right?
Yeah. So for example, if I scale this point here in
Yeah,
the first
this
quadrant,
wouldn't work.
this could go here, right?
This wouldn't work.
Yeah.
No, my reason for asking this was since the name is tangent cone, I was thinking that it should be a cone. That's why.
It is a cone. It is a cone.
But in this case, it's a half space, right?
Which case? Okay, someone else
In
is
this
saying.
case,
Um. Uh. In this case, the half space. Correct. Right.
so then how it is a cone then?
Okay. Uh. Okay. Let's see. So okay, well, let me. Should I finish this part? Or I'll just leave this. Then I'll remove this part because this, if for a general A, I don't think you can say anything.
मैं साले बड़ा बच्चा हूँ मैं बहुत गंदी शरारत करूंगा बंद
Excuse
कर
me.
दे
Can you
थोड़ी देर
please mute yourself?
ना भाई मैं बंद ही निकल रहा हूँ रुक जा
Okay, so let's see. So yeah, but I want you to think out loud here. So how would we prove that? So you are right. The question is, so here it looks like uh, sorry, from here looks like uh, the cone is uh, half space, or sorry, rather the other way around. My bad.
Half space is a cone. Yeah. Yeah, I think from I'm just thinking out loud. I think we should shift the origin to X star and consider all rays originating from X star. In that way, probably it may be a cone.
Yeah. So yeah. So I'm just let me state this. So how to prove that uh, this is indeed true. So how would you try to write it?
So we consider a point so that it's centered at X star, and we consider rays such as X minus X star from any point in the half space.
Okay.
So take any point, arbitrary point inside the half space, say X tilde, and then we consider X tilde minus X star, and then we try to scale that.
Okay. So one second. So T of X star S is uh, half space. Okay. So you are saying take some X in this half
So
space,
yeah,
right?
and then consider the direction X minus X star.
Okay.
And then if we can scale that by positive lambda, that direction stays inside the half space.
Okay. So okay. So X minus X star, that's in the half space, right? Just by definition.
Yes.
Okay. Um, okay. So what can we say about this?
Yeah, so if lambda is zero, when then the direction is not reversed and it's continuing inside the half space, right?
If lambda is
Greater than equal to zero, then
right.
that direction is not reversed, right? And it stays inside that half space.
No, but that's what you want to prove, right? So how would we write it?
I'm not sure at this means how to answer this.
Okay, any thoughts?
Yeah, I'm not sure in this. This is intuitively true, but we have to formulate it in the framework of a code.
Yeah, so why, yeah. So here in this case, what we have to show is the equivalence, that this actually happens to be a half space, right?
Yes.
So how would you characterize this half space in this case?
We need to find a normal, right?
Okay, so what will be the gradient at this point? So if this
Yeah.
let's say this curve is g of x is equal to 0.
So this will be gradient of g evaluated at x star, right?
Yeah. So what can we say?
So the half space is okay. Yeah, so such that d transpose this gradient.
Okay. Let's be a bit careful. So this is the gradient. The normal will be here, right? So normal has to be orthogonal to this,
Okay. Okay.
right?
Okay. So we have to consider any point inside that plane, right? Inside that half space.
Yeah. So
So that
yeah. So if this is the direction along which tangent is there. So how can we express this?
so if we take any point along that plane, tangent plane, suppose x minus x term, that should be orthogonal to gradient, right?
One second, one second. So are you you are saying this x star, you find your x my x such that you drop a perpendicular
No, I'm telling if you go along the tangent plane,
along the tangent plane. Okay.
and so consider a vector that originates from x star and goes along that direction either way. So that should be perpendicular to the gradient, right?
So tangent plane is this.
Yeah.
So if I go
So
here,
will that
that
help
will be
in characterizing?
collinear with gradient, right? Gradient g of x star.
Why should we call the gradient? Okay. The
Not the
gradient is
normal,
a
the gradient.
constraint. Right? Okay. No, but the gradient of that line gx constraint should be perpendicular to the tangent plane, right?
Sorry, the gradient.
The gradient of the constraint evaluated at x star, that should be perpendicular to the tangent line, right?
Gradient of the constraint at this point.
That
Okay.
should be perpendicular to the tangent plane, right?
Right. Correct. So then what is this?
So this is the tangent plane. So
No,
that's
but
what
so is this
I
correct?
was trying. No. This is not correct. This should be perpendicular, right?
Yeah, exactly.
It should be perpendicular.
Yeah, so a lot of times this confusion arises, right?
Yeah, that's what I was thinking. Yeah, this is perpendicular.
So, okay. So one thing is sorted out, right? So we can use the gradient to characterize this hyperplane now.
Yes.
Right?
We have a vector, right? Yeah.
Yeah, so what can we say? Gradient.
So now we can take any yeah.
But what will be this less than equal to?
This is less than equal to 0, right? Yeah.
Okay, yeah. So now what do we have to show this equal to? Let me copy this. Okay, keep it here only. So how do we do this?
So this half space is this is equivalent to this. Then we try to use the definition itself of the tangent cone to see if that lies in the half space. Take any sequence of points that approaches.
So you are saying we will take some sequence xk which approaches x star. Okay.
Yeah.
So basically some sequence here, so that will all be such that this is satisfied.
Yeah, at every instance.
Correct. Okay. But that's exactly what we want to show, right? I mean, isn't it a bit circular?
Yeah, it's sort of circular. Yeah. Just excuse me, somebody has come. Just a second.
Yeah, sure.
Go on, please. Hello. Yeah, I'm back.
Yeah, so I mean, as far as I know, I don't think in general it can be said so without assuming something about the set. So
Okay.
here it happens to be this convex set, and I'm just thinking how to state it. I myself am not sure, but I don't think in general it can be said just like that without saying anything about the set S, without saying okay, where is the point x star. I don't think
Okay.
because
means we cannot assert right from here that it's a cone, right?
Cone is fine, but why is it a half space? That is, I'm just thinking if I can prove this from this pictorial argument. I'm not sure if I can write it just like that. Cone is clear, right? Because you can just put this tau k to just scale it. So, for example, if you want instead of d, if you want the lambda, so you just put a tau k by lambda.
Yeah,
so
that is evident.
So cone,
is evident.
the fact that it's a cone is straightforward.
That's it.
But the reason for half space I told you, right? So the thing is, it really depends on the specific form. I think I drew this case where I had a case like this, right? Versus, let's say, a case which is just this plane. Oh, sorry, not this plane.
Yeah.
Yeah, this is fine. This is fine.
This should be fine. Yeah, this should be fine.
Right. So if it is something that is affine, it's a bit tricky to say. But if it's something that contains this, how do I say? I mean, it is in this case aligned to these axes and passing through this. In this way, then you can say that all the points are going to be contained in this.
Yeah, means it looks a kind of contradictory because at one we can see that it's a cone, but still we are not able to prove that the half space itself is a cone, right?
Yeah, so what I'm trying to say is it's like at least for this 2D cases, if I have this bias term to be 0, then it's pretty straightforward. But if the
Yeah,
bias term, if
yeah,
it's
that is
shifted, if it's some affine half
affine.
space,
Yeah, some
then
affine.
it
Yeah.
doesn't have to be true. That I wrote,
Hmm.
right? I mean, I think I removed it, but I'd written that A transpose X less than equal to B and A transpose lambda X less than equal to B.
Yeah, that was clear.
Right.
That
So
was clear. That
this,
was clear.
yeah. So this lambda,
That was perfectly clear.
yeah. So I'm just saying that this translates to this possibility wherein if I have this affine half space.
No, that it will settle the issue if we can center the half space. Means, as we can see that if that factor b is 0, then it's fine. So that we can, if we can recenter the coordinate system on the x star point, then it should be okay, just as before.
So okay, just a thought I had just now. In this particular case, if I think although we haven't proved this, but this set is S, right? This whole set, it's a convex set.
Yeah, yeah, means a half space, right?
Yeah, so this is a supporting hyperplane.
Yeah, these are supporting hyperplane.
So that is precisely the region left to it is precisely my half space, and that happens to be my cone.
Yeah, yeah, okay, okay, okay.
So, but then I have shifted the burden to proving the separating hyperplane, at least for these convex sets.
Yeah, yes,
So,
yes,
yeah, in
yes, yes.
general, I don't think such a statement can be made, at least not that I'm aware of. But yeah, thanks for the question. Yeah, I'll just check it up and see if we can prove at least in some conditions.
Okay, okay, fine, thank you.
And yeah, I mean, so I'm also thinking out loud. Okay, if you do spot any mistakes, please let me know in the reasoning that I've given.
Yeah, from the looks of it, I think it's just definition, so there shouldn't be any mistakes as such. But I'm thinking we need to tweak the definition somehow to make the statements kind of match each other. I think so.
Yeah, I have a feeling that I need to say something about the set S, and if I just give any arbitrary set, then
Yes.
it's going to be very difficult.
Yes, yes, some things, yeah.
But this was not your main question. I think there was something else that you were asking. Something about the intersection of the tangent cone of the intersection of the
No,
sets.
yeah, I was asking, yeah, the reason for the constant qualification and how it affects the formulation of the KKT condition. That's what was my main question.
How it affects. So without that, without the constraints, or maybe let me just write this down. So at least I hope that the basic idea is clear. Why do we want constraint qualifications? I mean, forget about KKT, but why would we want KKT? Sorry, there's constraint qualifications. Is that idea clear?
From my understanding, it is required because we want an algebraic characterization and the geometric characterization to match. Because what he said was the algebraic characterization may not be unique always. We
Yes.
want a characterization that uniquely captures the geometry of the convex, I mean, the optimization problems. Is this true in thinking that?
So that is part of it, correct? That is part of it. So there are 2 points. So why we need constraint qualifications. Okay. So
Yeah.
first thing that we would, yeah. So we want. So before that, let me state the optimization problem. Just some for some f and some constraints. Okay. So
Yeah.
this yeah, let's call each of these sets as SI. Okay. So our feasible region.
So SI are the
Yeah, SI is basically all x such that the ith constraint is satisfied.
yeah.
Okay. So feasible region is the
So
intersection of all these regions. So what we hope for is the tangent cone at a candidate point, at a feasible candidate point of the intersection is same as the intersection of the individual tangent cones.
Yes, yes. Yes, this is precisely the definition for CQs to hold.
Yeah, so both the things. So what you said is also very important. So another thing is, this is one thing, and also additionally, I also hope that the gradient of the constraint corresponds to the normals at
Yes.
active surfaces, right?
Yes. Means constraints which are active, right?
Yeah. So what we want is, in addition to this, is we want in addition we want the tangent cones to look like, so let's say Si corresponds to the constraint Gi. Okay. So okay.
Yeah, so this I is for the active set, right?
So the thing is here, so there are a few steps that are being mixed up with each other, but yeah, you are right. So we are looking at the points on the boundaries of the constraints. And why is that?
Because otherwise the intersection doesn't make sense, right? Because we have the whole subspace Rn is a
so if I have a point here,
in the other case.
Yeah, right. So if I have a point here, so if a constraint is inactive, let's say if a constraint is inactive, then tangent cone is the whole space, right?
Yeah.
Right. So that's why we that's why we didn't mention that. It doesn't make sense, right? Because then any D can be satisfied. D and minus D both satisfy, in which case it will be 0.
Yeah.
Right.
But anyways, the S spaces are itself subspaces of the Rn, right? So it doesn't matter if the whole space, we are taking intersection of the whole space.
Yeah. Correct. So let me modify this intersection I with I, where I corresponds to the active constraints. Right, so I'll remove this. So or it is for an inequality constraint. So this is for inequality constraint, and the next thing I'll write is where it's an equality constraint. So in this case, we want this, right?
It should be equal to 0. Yeah.
And just to give the nice simple example that he gave in the lectures, corresponding to this case equality constraint, h of x equals to 0 if and only if h of m
opposing inequality constraints, right? Opposing.
Yeah, even before that, I was just saying what you said. So
Yeah,
therefore,
specifically this I had the doubt.
yes. So is the doubt about this if and only if direction?
No, I am. My doubt is regarding he put this example and then he says that our algebraic constant may not always uniquely classify a geometric set of points. This is where my doubt was.
So this is all he's trying to say. So what he's saying is, first of all, you agree that this statement is true?
Yes. This equivalence is true.
Okay,
No issues.
fine. So what we'll do is we'll take the gradients in both the cases.
Yeah.
Okay. And these are all scalar, by the way, for simplicity. R to R or Rn to R. Okay.
Yeah.
And clearly this power here, just raising this scalar h of x to the power m. Okay. So if I take this, if I compute the gradient in this case, first case, h of x is 0,
Excuse me.
that is nothing but saying gradient of hx equals to 0. And what
Yeah.
about here?
Yeah, here it will be m minus 1. Yeah, m into m and then the gradient of x. Gradient
Now
of hx.
in this case, this is already 0
Yeah.
because h of x is 0.
Mm-hmm.
Right, so this whole thing is 0. So what we did was we took the derivative of this, equated to be 0, and the quantity on the left is the normal that we would expect, right? The surface normal.
Yeah.
Here we were hoping to find the same surface normal,
Mm-hmm.
right? But we didn't get that.
Yeah, because h of x is additionally coming in, right?
Yeah, so it is 0 because of the fact that this is 0,
Yeah.
not because of this being 0.
Yeah, it's sort of like we are introducing additional roots into the system.
I mean, so this is just one way of putting it. In general, what we are saying is you may not know which algebraic way you are representing the constraint, and hence you may expect that you are really the representation is not minimal in some sense. For example, in this case, polynomials is one way to put it, because the constraint is equality constraint.
Yeah. I get it.
So when we take the gradient, we would expect to precisely get the normal. Okay, but then we don't get the normal.
Yeah.
Okay,
Yeah,
so just to avoid these ambiguities, so we want both. We want the tangent cone of intersection to be intersection of the tangent cones,
right?
And we want the directions. Sorry, we want the directions, which basically the elements of these tangent cones, to take this form that we expect them to. Right. So the way we have represented our constraints, they indeed look like this, or like this, and when you look at the elements that are tangent at a certain point on the surface, we indeed get what we would expect. So the gradient is here, any point is making an obtuse angle here, right? Any point in this, on this side of the hyperplane, and here there's only two possibilities, right? Because they have to be orthogonal to this.
Yeah, in this case, as we have put it, it is correct. But yeah, the situation.
Yeah, so I could have equivalently written this line. This is h of x equals to 0. I could have morphed this into something else. So now I have scaled my gradient with certain other factor, right? So it will no longer look like this. This won't be my normal. This won't be my normal direction as I would expect. I'll get something else.
Okay.
Is it fine?
Yeah, it's somehow it's much more clearer now. Yeah, but the point is we do not know what is the correct representation, that a priori, right?
Yeah, so that's why we are putting some sufficiency conditions. So as of now, we have not seen, except for one case, why certain constraint qualifications work. We did see one proof. We'll come to that. I think there is a proof, very simple proof of f is convex. Then if you satisfy these constant qualifications and KKT conditions, then you are good to go. So the candidate part
That
is
proof he
okay.
mentions.
So
That proof he mentions. Yeah.
But okay, maybe, I mean, before even I go there, uh, it just provides some simpler condition for my candidate point to satisfy, to be said, okay, at least this is to be satisfied if I want to consider a point as a local minimizer. So there itself is important. So in that sense, it is not a sufficient condition, but I was using the word a bit loosely. But it's just one way to ensure that indeed these forms of tangent cone are manifested.
Yeah, got it. Yeah. So this is very important for characterizing those optimal points, right?
Yeah, so this
When
is
we are
how we'll
moving
get the
further
KKT
along.
condition. So if you recall this, if
Yeah,
once
this one.
we write it like this, that the constant qualification ensures this representation for the tangent cones, then we can immediately derive the KKT condition using Farkas lemma.
Okay. Yeah, got it. Now I get it. Yeah, he mentions this. Yeah.
Okay, so is this fine? Any other questions regarding?
No, I'll ask a little small doubt before we leave on to the subject. So he just mentions a powering thing where this fails. So there can be many other instances, right, where this fails, right?
Yeah, so yeah, correct. So just off the top of my head, let me see if this makes sense. So what were the two ways in which we wrote the linear programming? This won't exactly work because the feasible region changes. Uh, yeah, this won't work. Yeah, this won't work. Let me see what other example do work. Okay, the feasible regions are same, but do you have any example in mind?
No, I do not have right anything top of my head at this point.
I mean, there are some trivial ones, but like you can just scale a constraint by some non-zero scalar, some non-zero positive, non-strictly positive scalar. That, but I don't want to take that simpler case. I'm just wondering if I can represent. I think. I mean, the only thing that comes to my head really is the following. So I was giving this example of h of x is 0 if and only if h to the sum m is equal to 0, right? So in general, I could just say some bijective mapping.
Yeah.
So yeah, I mean, in this case, polynomial is one easy one to see because the equality is with 0. But in general, I could pick up any bijective function such that it still remains 0. But again, I mean, then you'll have to, specific to h, you'll have to come up with the function phi.
Yeah, I get the basic point. Yeah, get the basic idea.
So
it's clear.
Yeah, just to expand a bit on that, what will be the gradient of this?
This will be phi prime. x, h of x, sorry, and gradient of h of x.
Right, so basically this is the normal we are getting. Should be
Yes.
getting this normal.
Yeah. Yeah, I got the basic idea. Yeah. And again, means he mentions the linear independence constraint qualification, but somehow on the slides I also saw a Mangasari and Fomovich, but he didn't mention that in the lectures. I don't know why.
Yeah, just let me recall. I don't remember the criterion for that. So since it's already roughly 50 minutes into it, so what I'll do is we'll just solve some questions and then come back to it.
Yeah, I think that is better. We'll leave the discussion at that. Yeah.
Okay.
So I got the basic idea. It will take some time to sink in gradually. So no
Yeah, I
worries.
just only way is so solve few problems, and but really this is the key. So just to add one more point, I really like this example that he gives. It's a very simple example.
Yeah, this is also good example. Yeah, it's a good
So
example.
I'll just use different colors. So here, and so these are circles with the interiors. So this is the point x star. So you see that this gradient and this gradient, they are linearly independent, right?
Linearly
But
independent.
here they
Yeah,
are collinear. So in
yeah,
this
yeah.
case, we indeed expect the tangent cone of the intersection to be the intersection of the two tangent cones. But
Yes.
here, in the second case, of course, it doesn't happen. And
Hmm.
so we see what is really helping us do that.
Yeah. Yeah. So suppose we had two constants, we should leave out one of those, right? S2s, right? S1 or S2, right?
Yeah, I mean, yes. So, well, the thing is, this problem, there's only one candidate. So, there's really nothing to check. But in general, yes, there has to be some way to reduce the redundant constraint, so to speak. And
Okay.
one way to capture this redundancy is take these gradient directions and see how if they are collinear or not.
Yeah. The link. Yeah.
Okay, so let's get started with questions. So I'm looking at a circle of radius 2 centered at origin. That's my set. Right.
Just give me a couple of seconds. I'll just pull up the answers which I've written. Just give me a couple of seconds.
Yeah, sure.
I'm just logging in. This is week 8, right?
Yes.
So in this week, this is the only question I got incorrect in the whole assignment. I don't know why.
Okay. Yeah, let's go one by one and see which ones are correct or not correct and for what reason.
Okay.
Okay. So what I will do is I will remove this terrible drawing and draw a proper one.
You are using notability, right?
Yeah.
So you can draw very good circles there. Yeah.
So I hope this is somewhat better.
Much better.
Right, so this is my x star. Okay. Yeah, where is point A? Point A is maybe somewhere here.
Yeah.
Okay, point P is 1 1, so that is somewhere here. Okay, is this point even in the set C?
Which one?
The point C.
Point B, right?
No,
C
C
is not
is
in the
not
set.
there, right? And how about D?
No.
Okay,
And D is also not there.
right. So do we need to consider them?
Are we asking for tangent cones
Yeah,
in
tangent cone.
which of the following is yeah, we should consider because it's an entire half space, right?
Yeah, correct. You're right. Yes. So we should consider. We should not eliminate them just like that, just because they are not visible.
Yes.
Okay. Good. Okay. So let's start with the point A. Okay. Even before that, we'll just pictorially see. So what is the tangent cone here at this point?
Yeah, so it's everything below that point, right? Yeah.
Yeah.
This is.
So okay. So tangent cone is what?
It's a half space, so it's so the gradient is x. Yeah.
Is this fine?
So it's x is equal to 1, right? Yeah. So y is equal to 1. Sorry. Yeah, I cannot see that because just a second. Yeah, y less than equal to. Yeah.
Okay. So this is fine, right?
Yeah, this is okay.
Okay. So then which one satisfies this? So we just have to check this, right? This is our tangent cone.
Yeah.
So does A satisfy this?
Yes.
Okay. How about second one?
Yes.
Okay. How about this one?
Third one, no.
Okay. And what about the fourth one?
No.
So X is okay, but the problem is with the Y.
Yeah, sorry. Yeah.
So is this fine?
Y less than equal to. Yeah, that's fine, right?
Yeah. Right. And so if we look at where is C exactly?
Yeah, C is, yeah, so it's about.
Maybe somewhere here, maybe outside.
Yeah.
What about D? Oh, sorry, that is D.
No, C is,
That is D, and C will
that
be
is D.
somewhere here, maybe.
Or,
C, sorry. So it's okay, right?
yeah, it's okay. I drew the tangent plane on the opposite side. That's why it came out as correct.
The set is actually on this side, right? So I can approach. I hope you are able to see the blue color. I can approach like this.
Yes.
If the set were
Yes,
the
you can
circle was
approach
sitting at the top, then you are right.
Right. Yes. Got it.
Okay. Second question is again it's a 2D case and it's a box. And the claim is the tangent cone at this point half comma half is R2. So what do we do here in this case? So let's say this
So
is
it's whole of
extra.
R2.
Right. So this is true,
Yeah.
right?
Yeah.
And why is that?
Yeah. So this is inside, that lies inside the set.
Yeah, it's in the interior of the
Yeah.
set.
It's interior. It's in
So
the
more generally, you have to be a bit careful. You have to be in the relative interior. But here it's okay. We are not dealing with that case. It's just
Oh, okay. We have to be in the relative interior when the dimension is less than the ambient space, right?
yes, yes.
Okay.
So if this same thing, this 2D box, if that would have been put in the 3D space,
Yeah. Yeah.
so I'll have to take the intersection, right? So just have to be a bit careful there. So I mean, just to maybe add a bit. So what you have to do is you have to if to find the relative interior, I'll have to do the interior, that ball, whatever I consider, and the intersection with what?
The intersection into the set, right?
With the affine hull, right?
Yeah, affine hull. Sorry, affine hull. Yeah.
Because that will effectively tell me the reduced or the effective ambient space, right?
Yes. Yeah, the subspace dimension,
Yeah,
right?
yeah.
So is dot above S is a standard notation for interior? I did not see that in Boyd. That's what I was asking.
I think so. I mean, I am used to using this notation. Otherwise, or sometimes I also write just int of s.
Int is a notation I see most frequently. That's what.
Yeah, I mean s not s and the circle above is also I think fairly commonly used.
Okay.
So the third question says that I have a 2D case. I'm optimizing the variable of these two, function of two variables x. Where x is a vector of components x1, x2, and let me call that objective to be 2x1 square is a quadratic objective. 2x1 square plus 3x2 square minus 8x1 x2. Claim is x star equals to 1 1 is a local minima. So how?
So do we need to complete this? I thought of doing it by completing by square. Is that okay? Just for the simple case.
In general, yeah, you can just make a matrix and see from there. So we can do that also.
Okay.
So how will you do this?
So we can write the quadratic form expression. Right? Yeah.
So how will we do this?
So this should be 2, 3 on the diagonals.
Is this fine?
3. This is okay, right?
Yeah, it's okay. We'll still just do the check in case I have made any mistakes. 2x square minus, so this seems fine.
Yeah, this is okay.
Okay, so what do we do now?
So now we can check for the positive definiteness, right?
Yeah, okay, but okay, fine, yeah, sure. That's one way to do it. So we just that works. Uh, we already seen that, so let's just do it. So what will it be? Simply 2 minus 4 3, right?
Yes.
So is this PD, PSD,
Uh,
negative, negative, semi-definite,
2, 3, 6, 7,
indefinite?
6. It's positive definite, right?
Why do you say that?
So the Sylvester's criterion, right?
Okay. Okay. So
Yeah. So
what do you
the
do in that case? You take this.
so
The
two
difference
is
is
two
equal
is
minus.
positive. Yeah.
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 Then
2 is positive, and you take then it's just 6 6 plus 8, right?
yeah.
14. 8. Yeah.
Okay. So
They're all
lambdas are not
positive.
zero basically.
Yes. Yes.
Is this one plus 6 minus 16? Yeah, minus 10. So lambda is 2 and 5, right? No, no. Lambda is not 2 and
Yes.
5. It's not 2 and 5.
Uh,
But it's not
it's
0.
yeah. It's not 2 and 5. Yeah.
Okay. So this is. But are they positive?
Uh, wait. The product is negative, and the sum is also negative. So that means, yeah, both of them cannot be positive. Yeah.
So what? Okay. So what can we say from here? You cannot conclude anything, right?
No, I cannot conclude anything. Yeah.
Hmm.
Cannot conclude.
Are you sure?
Yeah. Maybe not.
No, we can
This is
actually.
teasing me,
No. So
teasing my
I'm just trying. So
knowledge.
this is
Yeah.
just to recall, not to tease you, but just
Yeah.
to.
Yeah. I'm forgetting those things actually. That's the problem.
So that's okay. So
It's
lambda
so
1 is
much.
0, greater than 0, lambda 1 is some less than, lambda 2 is less than 0.
Yeah.
So
So
what does this mean? It's indefinite.
it's indefinite. Yeah.
Okay.
Oh, I have to study linear algebra a lot. I'm not getting time. Sorry for that.
That's okay. Anyway, we'll keep practicing questions. It will be
Yeah.
easier as we go along. So that means it doesn't. So second order condition, actually so by second order necessary condition, x star is not local minimum. That's okay. Uh,
Yeah.
we will
That's
we
not
will
local
we will
minimum.
we can even do something simpler. We can just take the gradient of fx, gradient of f at x star. That will be simply 2 minus 4 3 x1 x2 at 1 1. So what is this? Minus 2 minus 1. It's not 0,
Yeah.
right?
Yeah. Yes.
So that's the problem.
But here in this case, SONC was already a overkill, so we can just check it from the first order condition itself. But it may not be the case. We may have to go to the SONC, right?
Yeah. Oh, I forgot a factor of 2. Sorry. Sorry, what were you saying?
No, I'm saying that in this question we can just conclude by the first order condition itself, but
Yeah.
it may not be the may have to go to the second order conditions, right?
Yes.
For completion.
I mean, I answered in the negative here by F1C, so I don't have to worry about going to the
Yes.
second
That's
order.
fine.
If
That's
it
fine.
were satisfying, then I have to go to the next conditions,
Yeah.
SONC, and then see what happens there. I mean, this is just to maybe get a bit ahead of ourselves. This is not a positive definite or positive semi-definite matrix, right? So that's not a convex function. So it's really
Yeah,
a
that's not a
question in
convex function.
disguise about convexity. So
Okay,
if
okay.
this Hessian, which is this matrix,
Uh-huh.
if this happen to be either positive, at least positive semi-definite, then we can safely say it's a
Yes,
convex
yes,
function, and
yes,
then
yes, yes.
things will be much simpler. So
So this may be a saddle point, right?
yeah,
For
yeah,
instance.
it is a saddle point.
Yeah, it's a
So
saddle point.
one direction, in one direction
Yes,
you
yes,
can increase the value, one decrease the value. So
yes, yes. This question asks for checking which of the constraints are satisfied.
no, not constraint.
Uh,
It's asking something else.
no, question number 4, right? 4, right?
Oh, okay.
It's how many constraints are active. You are going to 5, I think, right?
Yeah, okay. So maybe we'll just come back to 4. Sorry.
Yeah, we will come back. We'll come back.
So the question 5 is just asking, I have some objective f of x. I have a bunch of constraints, the 3 constraints that I have written here. I have a candidate point, and I'm seeing for this point if the LICQ constraint qualifications hold or not. So LICQ constraints are something that you've already seen, which says that the gradient of the function at this point, which is the f of x star gradient at that point, is some linear combination of the gradients of each of these constraints. That's all we are trying to see. Okay.
Yeah.
So for by the way, before even beyond that, actually we can say which constraints are active. So actually we need to check that, because we only check for those.
Yeah, we need to check. Yes, we need to check for those.
So only for those active constraints we will check. So which are the active constraints in this case? So let's just see. Let's call this
This
corresponding.
is active.
So let me call this g1 of x less than equal to 0, g2 of x less than equal to 0, and g3 of x less than equal to 0. So what happens at g1 of x star? 1 and 2. So
So that
3
one is
plus
active. 4 plus 7. Yeah, that is active.
right, 3 plus 4 minus 7 equals to 0. Okay, what about g2?
G2
1 plus
is
3
4, 12. That is also
4
active.
minus 13 equals to 0. And how about this? 5
G3 is
plus
not active.
4 minus 20 is not 0. This implies the sets that are active are 1 and 2, right?
Yeah.
So we want to check whether gradient of f at x star equals to some linear combination of where I in a of x star, right?
Yeah.
Right. Okay, so what are the gradients?
So we just need to consider the first and the seconds. So that is 3, 2, first one.
Okay, I think I'm mixing up two things. I'm not sure why.
Yeah, you do not need to mention that statement. Like gradient of fx is no need to mention that, right?
So
Yeah.
I'm sorry, I'm thinking about something else. I will
I was
just,
confused regarding that.
sorry, I will rewrite this. I don't know why I said this. So what I wanted to say, we want to check whether this set is linearly independent, or these gradients are linearly
Yes, the
independent.
gradient set. Yeah.
Right, so yeah, F is something we're not looking at right now. I just jumped to KKT for some reason.
Yeah, that's what I was thinking.
So the G1 and G2, these are the constraints we are interested in. So this is our G1, 3x plus 2y minus 7. So what will be the vector, gradient vector, 3 comma 2, right?
It's a constant gradient vector, right? 3 to linear function.
Yeah, 3, 2. And what about gradient of G2 at x star? That's also a constant vector, right? No, that's not a constant vector.
No, that's not constant. That is 1, 2y, right? 1, 6y.
Correct. 1, 6y, and because we are looking specifically at a candidate point 1 comma 2, so we can put 1 comma 6y at 1 comma 2.
Yeah. By the way, I was just thinking maybe it's not a specific to the question at hand. So if we have a large number of constraints, so do we have to enumerate each of them at each point and see which of them are active and which are not active? All those things.
Okay, are you saying numerically how the consent qualifications are checked?
Yeah, means I'm thinking if suppose the constraint set is huge, then it becomes infeasible to check for the active set at every point, right? So how do we approach the problems then? That's what I
Yeah,
was
I
thinking.
am not sure. I'm not sure numerically how it's done.
Okay.
Maybe what I think what might be happening is, but yeah, that still doesn't help. So there are these methods called active set methods. They find which constraints are active, and then only uh, consider those constraints and discard the rest for the reasons that we saw in the lecture. But what you asked is still a problem, which is that you have to check invertibility of that matrix, where each column is one of these gradient vectors.
Yes.
Uh,
It becomes intractably large, right?
yeah, I'm not sure. Not sure if there is a way to escape this invertibility check.
Because he mentions, Professor Ankur Kulkarni mentions that these problems of KKT always have a combinatorial flavor to them, since we're
Yeah,
always seeking for constraints which are in the active set. So
yeah,
that's why I was asking. Okay. Yeah.
yeah. I mean, off the top of my head, I don't think I know how to do it.
Okay. Yeah.
So these two are linearly independent, right?
Yeah.
Okay, coming to question 4. So I have 2x1 plus 5 is 2 less than 7. So these are my constraints, and question is pretty straightforward. How many constraints are active at x star is 1 comma 1? So let's just follow the same convention. Let's call this g1x less than equal to 0, g2x less than equal to 0, g3x less than equal to 0, g4x less than equal to 0. Okay, so what is g1 of x star?
It's 0.
How about g2?
That is less than 0.
How about g3?
That is 0. G4 is also 0.
So there are 3 active constants, right?
Yeah.
Okay, question 6. So there is a function that is convex. X1 star and x2 star are local minima. Claim is that the values are equal. So x1 and x2. Is this true or false?
This should be true.
The reason for this?
The reason is since it's a convex function, it should have one unique minima, right?
Uniqueness need not be. For example, I can.
But the value of the minima should be unique. Right?
This is
Yeah. That's true. Yeah, that's true. The value of the minima, the function value at the minimum point.
But why is that the case? Why should it be value should be minimum unique?
Why should it be unique?
So is this clear now? So because every local is a global minimum.
That's true.
Right. So this is the way argument needs to be made. So because any local minima is a global minima, if I say there are multiple local minima, they all have to have the same value because they are all global minima.
Oh, okay.
Otherwise, it becomes circular, the reasoning.
Yeah.
Okay, we have our hinge loss.
Yeah, this is a hinge loss function.
It has a unique global unconstrained minimum. I am claiming this is true, false.
Yeah, this is true, right?
Unconstrained minimum.
Unconstrained.
Actually, consent also it depends.
Yeah, this is
on-
false. This is false. Yeah, this is
false, right?
false.
Because
Yeah, true.
any x greater than equal to 1
One. Yeah.
is a unconstrained global minimum. So by the way, this is also convex function,
This is convex. Yeah.
right? So just to answer your you were asked. I mean, I know you said by mistake, but just another example, right? Where the global minima is
Yeah.
not unique.
Yeah. Yeah.
Okay, so there is a function f for the next question such that there is a point x star at which gradient is 0. So we'll just go one by one and we will see which one are correct. If f is convex, x star is local minimum. F is non-convex, x star is local minimum. F is convex, x star is global minimum. And same thing in the non-convex case. Okay, so yeah, so how do we go about this?
So for the first case, it's true by definition, right?
Okay, so let's be a bit careful. So f is convex. So what can we say by definition?
Every local minimum is a global minimum.
No, that's fine. But we are asking about something else, right? We just are given a first order necessary condition.
Okay. Then we have to okay. Write the gradient.
So what is this?
Yeah.
It's okay, right?
Yeah, that's fine. So that means it's true, right? A is true.
Yes. So A and D are true, right? Oh, sorry, not D.
Yeah.
A
C.
and C are true. How about B and D parts?
Yeah, B we cannot say because if it's a non-convex, then F0 doesn't guarantee anything. It can be a saddle point, right?
Okay, so can you give maybe some example? It's here. Is it given to be?
Yeah.
Okay, well, but just for the sake of discussion, we can just come up with an example. Maybe if you have any
Take as
example.
fx is equal to x. Fx is equal to x cube, right?
Yeah, that works. Right, so obviously this is so this is okay, right?
Yeah.
Okay. question 9. So there are 4 questions left. Yeah, so we have some time to solve some other problems also. Let's see. Question 9 says I have 2 sets. So these are circles, I'm guessing. Yeah, circles with so these are circles with 2 different centers but same radii. Okay, so we have the figure 8.
Yeah, so this is the same example we discussed.
Correct. Yeah. Okay, so is S1 S2 point of interest is x star, which is the origin. Right, it is also, by the way, the only intersection point, right?
Yeah.
So what will be the tangent cone?
Tangent cone will be a singleton set, right? Just of 0.
Okay, equals to 0. Yeah, that's correct. So this is just straight from the class, right? I mean, I'm not writing
Yeah.
anything further because it's exactly the same thing.
No, it's not required.
Okay. X star and X star star are two. So the next question, X star and X star star are local minima of a convex function f. Then which of the following are global minima for this function? Yeah, so here how to go about this?
So this is the two local minima. That means this is a unique global minima, right?
So again, unique in the sense of value, not the minima.
Yeah, means okay. Then which of the
So
following? So X star is a global minima,
and X
since all
star is
local
also
minima are
X star
global.
star is also. So let me just
Yeah, both of them.
so X star star global minima. Why is that?
Yeah, because in a convex function, any local minima is a global minima, right?
Yeah, because f is convex, right? That's what we saw just now above.
Yes.
Because f is convex. Okay. Now can we say anything beyond this?
Yeah, since the function is convex, then
So any convex combination is also working, right?
Yes. So in this case, the shape of the function has to be one of those kind of where the bottom is flat, horizontal, right?
Yeah, there are some parts which are like this.
Yes. Otherwise, how can it be?
Yeah. Okay, question 11. So in this constraint optimization problem, we say that there is a candidate point that satisfies the KKT condition. Claim is that X star is a global minimum. So is it true, false?
So this is true.
Why is that?
Yeah, since we have to check for the conditions for the KKT condition to hold, whether the function and the constraints are convex.
Yeah, so this F is convex. Constraint is convex.
Yes.
Right, so optimization problem is convex. So KKT condition is satisfied, so that's why it's true. Okay.
Yeah.
Okay, last question from the problem set. So your function defined R2 so I have to minimize this objective. Such that and let's say X star is the optimal solution. Find the value of the function at this optimal point. So how do we go about this?
Here we have to calculate, we have to write the Lagrangian.
Yeah, this is slightly long compared to others, so let's just write
Slightly
it.
long. Actually, it's good that there is a question like this, then we have a good practice.
Yeah. So what do? We write the Lagrangian, right?
Yes.
So Lagrangian is x1 square plus x2 square plus lambda 1 times 3 minus 2x1 minus x2 plus mu 1 x1 plus x2 minus, there's no vector, I'll just put lambda in mu. Okay, I've written my Lagrangian now. Anything else I need to mention?
Yeah, now anything? Yeah, lambda greater than.
So this is important, right? Complementary slackness is also important.
Complementary slackness. Yes.
Anything we can say about the functions?
Yeah, we can plot it and check. It's a circle.
Yeah, so I mean it's a
level
convex
sets of
function.
circles. Yeah, it's a level sets of circles.
And this is also convex.
Yeah.
So we are looking at a convex optimization problem. So if x star satisfies KKT, what can you say?
So we have found a global minima, right?
Yeah. So here global local doesn't matter, right? Because it
doesn't matter. Yeah. Yeah.
Okay, so having made that remark, let's just so having said this, what do we have to do?
Now you have to take the first thing is to take the gradient of the Lagrangian, right?
Yeah, so what we'll do is we'll take the gradient with respect to x. And so what do we get?
So this is 2x1 minus 2 lambda plus theta. Yes.
2x1 plus 2x2. No,
Yeah.
you have to be careful, right? You can't just, there are two variables.
Yeah.
So let's just do, okay, what's wrong with this? Yeah, so let's
sorry
just,
about that.
Yeah, no issues. The eraser is sometimes not getting selected. Yeah, so what can we write? 2x1 minus 2 lambda
2 lambda, yeah. Plus mu.
Similarly, 2x2 minus lambda plus mu, right?
Yeah.
Okay, so what else can we say from here?
So since I have gone this way, I first check the values while lambda is equal to 0. Since there are two possibilities in the this thing, complementary slackness condition.
Right, yeah.
So I first check the lambda is equal to 0. And try
when
to
you say
solve
lambda equals 0, what do you mean? I didn't get you.
No, in the complementary slackness, we have the product of two terms is equal to 0, right?
Right.
So one of them has to be 0.
Okay.
Or both of them can be 0.
Correct.
So I just first started out with the case lambda is equal to 0. And then tried to solve for x1 and x2. The solution came out. So I didn't check the other conditions. That's what I was trying to say.
Okay. So let's just continue with what we are doing here. Okay. Right. So what can we write from here?
So this is, yeah.
Right.
Yeah.
And here?
It's lambda, yeah, the minus mu by 2.
Okay, now what can we do?
Now you can do one thing. You can put it in the complementary slackness.
No, we can do something even simpler. So, what I'm suggesting here is something that you'll have to do. That I mean, not just this week, but I think since we are a bit out of time this week, I'll solve some more problems and you'll see. So, we need to use many things here. For example, we can use this and this. Sorry, not the first one, just the second one. We have to check that it's feasible also, right? Not
Feasible,
check. I
yeah.
mean, we have to use the fact that it's a feasible. The point is feasible.
Yes.
Okay. So what we'll do is we'll say x1, x2 is feasible. This implies x1 plus x2 is 2, right? Is that the constraint? Yeah. So what can we say? Lambda minus mu plus lambda by 2 equal to 2. Anything else
Yeah.
you can say?
Not sure about anything else. Maybe we can simplify this equation and see.
No, so now your idea of slackness is going to be useful. See, ultimately, what we have to do is once we write the Lagrangian, we have this nice set of equalities that we have a system of equations that consists of this equation, this equation. So, okay, so note that how many unknowns are here? How many unknowns are there?
4 unknowns are here.
Lambda, mu, x1, x2, and x1, x2, lambda, and mu, 4, right? And how many equations do we have?
We have feasibility.
Yeah, feasibility is there. Okay. Then there is one complementary slackness, and then there's this, right?
Yeah. So there are 5 in all, right?
If for now, let's just ignore the inequality one because we want to compute the exact value.
Okay.
Right. So
1, 2, 3, 4. Yeah.
So we have used these two. We have used this one, right? x1 plus x2 equals to 2. This is the only one that's left. Complementary slackness.
Yes.
Right. So now we will use complementary slackness. What you said is something that has to be done. Sometimes that has to be done. You don't have any other information and you have to go case by case.
Yeah.
Which of these lambda is a 0, non-zero. So it's not that.
No, but since I found a solution and the convex problem admits only one unique solution, I just straight away say that it's a.
Yeah. That's true. So what was this complementary slackness condition? Lambda times 3 minus 2 x1 minus x2. 3 minus 2 x1 minus x2. Okay, and what is x1 and x2? We have it here, right?
Yeah, so I have to substitute those, yeah.
So 2x1, which is nothing but mu minus 2 lambda minus mu.
Yes.
And you have minus lambda by 2 plus mu by 2. Okay, so what do we get?
This is lambda 2 lambda, 3 lambda by 2. Okay.
So here from this case, what can we get?
Lambda minus mu plus lambda by 2.
So from here, what can we say? 3 lambda by 2 is 2 plus mu, right?
Yeah, substitute that.
So we will just put that here. So what we will do is 3 by 4, 4 by 3, 4 by 3 into 2 plus mu minus 1 by 3 2 plus mu by 2 goes to 0. Oh, okay, oops, I think I wanted to write lambda also in terms of is that fine?
Yeah.
So okay, so what do we do now?
So now the thing is that the simplify, right?
Yeah, I think mu comes
It's
out.
2 plus mu.
I mean, I'm not sure. I'm just writing what I got directly. I may be wrong in this. Just check it out. And if I put
Yeah,
mu as minus 2, then lambda is 0.
Obviously, since 2 plus mu is a factor, mu definitely is a minus 2.
Yeah, I mean that's one possible solution. Yes.
Yes.
Am I getting anything else? I think everything else gets cancelled out.
Does mu get cancelled out in the second factor? It's minus 4 by 3 plus mu. That means minus 1/3. Minus 1/3. Then it's another minus 1/3. So it's minus 2/3.
I might have made a mistake here in the algebra. Let me see. So till here the relations that I found are clear, but I might have made a mistake in substituting the values. 3 minus 2x1
Yeah, means
minus x2. 3 minus let's just go ahead with this. This is one possibility, and I think what you said that has to be used anyway. The function f is convex, so as long as I found one candidate that's satisfying this KKT condition, I'm good to go.
yeah. And the second factor will only evaluate to a constant, right? Otherwise, we would have another factor over mu over there.
Yeah, I think I'm afraid I probably messed up somewhere here.
Yeah, means I was just, maybe it's no use brooding over that. Yeah.
So x1 star x, if I put lambda as 0 and mu as minus 2, so
It's
what
1,
do I
1.
get? 1 1. Oh yeah, it's 1 1. Yeah. Okay, so f of x star is simply 1 plus 1.
2.
Right? Okay.
Yeah.
Stop sharing my screen. And also
So this is a